I will give this talk, and today I would not talk about any technical things, just mainly, mostly about the philosophy and why I'm doing, and together with all my co-worker and Paul Bouguet, Lars Erdős, and Antti Noos, and Benjamin Schrein, and Ian Jin. So some of them, so why we study the problem, and because, for example, like Jörg keep on asking me that why we are studying such a technical question, and so I will try to be as much a philosopher as possible, but I don't know if I will be successful. Anyway, so here's a question. So I will start to define. So question, of course, this is well known to many people, but let me just go through it. And you start with symmetric matrix. And then you can take each metric element are the Gaussian random variables. And then you normalize the mean 0 and the variance 1 over n. So don't worry too much about this 1 over n. Oh, sorry. So this is, of course, is wrong. It's n over 2. Anyway, so you normalize correctly. Then once you normalize correctly, then you find your eigenvalue is between -2 and 2. And this is really for normalization purpose. So don't worry about this. And then the eigenvalue will be the older one. And so this is called a Gaussian orthogonal ensemble. You can define the Hermitian and the other ensembles. Now this will be called a Wigner ensemble if you don't take the Gaussian, but you take independent random variables. Okay. So this is what's called a non-invariant ensemble, because once you take this Hij are not Gaussian, then the distribution law of this metric H will not be invariant under the orthogonal group. So this is called non-invariant ensembles. And then the Wigner semicircle law says the density of eigenvalues is like this, is like a semicircle. So now we saw this many, many times. And then so you have n eigenvalues distributed here. You can see that, so the edge will be has much bigger gap than inside. The typical gap inside is 1 over n, and outside will be n to the -2/3. So the probability density of eigenvalues is called Pn lambda 1 to lambda n, and this is a law generated by the matrix element itself. So from here you can define the so-called two-point functions. Two-point function just means you ask the probability just two eigenvalues. So this means you integrate out the rest of them. But whenever you define this two-point function, you should symmetrize this eigenvalue. Otherwise, you always this lambda 1 and lambda 2 will be always the first one and the second one. But if you symmetrize, then you can think about this. This is the probability to find eigenvalue at one energy lambda 1 at the other energy lambda 2. So this is so-called two-point function. Okay. Now with these two-point functions, and then you want to rescale this two-point function because you want to understand the structure at a scale 1 over n. And then this is a famous calculation by Golding-Mehta and by Dyson for these circular ensembles. The two-point function has explicit formula given by determinant of sine kernel, and they are general formula for the general cases. And also this for the edge, you have this Tracy-Witten law, and this means the largest eigenvalue -2 is given by probability f beta of s, and this function is explicitly computable. All right. So now, so this was the one main question we already answered a few years ago, is this Wigner, Dyson, and the Mehta conjecture, and it says it basically says that for the Wigner matrices, it doesn't matter what's the distribution, you will always get the Gaussian behavior. And this was and we also extend this to a generalized case. This means the metric element distribution can be different. So this was the background. And then there are some independent work by Tao and Wu, and these cover a few special cases. And especially the Hermitian case was quite complete, but the symmetric case is just special cases. Okay. So this was a development up to a few years ago, and the upshot is really now you understand the matrix for the Wigner metric ensemble. You understand that why this universality hold. And also today, today I will not talk about why we are interested in this question of eigenvalue distributions. And there are lots of historical reasons. And for us, the main reason is because this seems to be a new class of a probability law. You can think about a probability law. This Poisson statistics and the Gaussian statistics has been around for centuries. And this is sort of a new class of metric law which is universal and which one can compute it quite explicitly. And also the most amazing is this happens for a highly correlated system, because most other universal laws are for independent systems, and this is a highly correlated system. And so that's why we make such a big effort to understand these questions. And then, so I'm not going to give you the more precise condition under what condition, in what sense this hold, but rather let's go on to ask a more general question. In a way, are there other systems also share these statistics, and then beyond this Wigner Dyson meta conjecture case, what other cases one might be able to do? So this is the main purpose of today. And so the other thing I want to mention is this so-called quantum unique ergodicity. And then now I will explain that why we are interested in this question and why this question may be related to the universality of random matrices. So this was, if you take a matrix of negative curvature, and actually they are more general formulation, but just take this case. So then you take eigenfunctions, then you can see that you take test function times the eigenfunction, and this is a smooth test function. Then it becomes just a volume element. This means the eigenfunction will converge to, actually there should be a constant here depending on how you normalize it. So this means the eigenfunction, it will all converge to a flat measure. So this is called a quantum unique ergodicity. And then the difference between this unique ergodicity and the quantum ergodicity is the quantum ergodicity is some sort of average version. So this statement is correct for a set of measure 1. Measure 1, I mean this except. And this is called the quantum ergodicity. The quantum ergodicity is much easier to prove, and there are many results. And there are also arithmetic case that one can do this QE, but we are far from any arithmetic case. We are sort of doing the opposite case. We are doing the case that it's a completely random case, so there's absolutely no, it's the opposite region compared with this arithmetic case. So now the question is, you can ask the following question. If the Wigner matrices and if this QE hold, so what does this mean? What does this mean by QE holds for the Wigner matrix? Just you take eigenfunctions, and then you ask yourself the eigenfunction at the end will be completely flat or not. So I want to compare this with the with this one. Okay. Oh, by the way, you should ask question because I don't have many transparency, and so I'm going to run it out very quickly. And so if you ask some question, so if you don't ask question, then my talk will finish in half an hour, and then I don't know what to do.
So flat is well defined. When you say you want the eigenfunction to be flat, how do you define flat?
How do I define flat?
Yeah,
oh, the flat, at least in the metric case, the flat is easy to say. Flat in the metric case, the eigenvalue they are n element. So for example, each one, of course, you can change a little bit. So you have to take you take a component, you take an average of a component, then it has to converge to a constant. Really converge to a constant. You have no choice. So this means flat. So of course the eigenvector, the component, if you look at each component, of course but if you take a local average, it will be flat. But you have to say this for each eigenfunction. You are not allowed to say, you're not allowed to average over eigenfunction, because average over eigenfunction, then it's much easier question. So this is what I mean by flat. Did I?
So each one will look like a random unit vector.
That's right. Each one will look like you take a random element from this orthogonal group. Then it will be flat. All right. So now I should mention this the related question about Anderson model and the quantum chaos. So the Anderson model, this was actually, since I was a student, this was a question many people working in math physics are wondering. And the reason was because the Anderson says the eigenvalue are eigenvector are localized, and then but then there's also opposite case of a delocalization case. So now the localization case was proved mathematically by Florix-Spence and Eisenman, Machranov later on. On the other hand, another important message is that eigenvalue statistics will be Poisson statistic. This was proved by Minami. On the other hand, in the delocalization region, this means that delocalization means the eigenvector will not look like that. It will be sort of flat. So delocalization means it's not concentrated in the region. It's just like that. And in this case, one believes that. Is this under Riemannian manifold? No. This is lattice. You take it on the lattice. So, well, of course, you can also do the continuum model on the Euclidean space, but we are not talking about manifold here. So this V of omega is a random variable. So it's easier to think about it on lattice because each lattice distribution are just independent. And then in the delocalization region, this means this coupling constant lambda has to be small and dimension has to be 3 or higher. Then one expects that the statistics were given by the Gaussian orthogonal ensemble statistics. And but of course, right now we don't even know if there's a delocalization region. So this is one of the key questions. And then, so if you look at this question and compare this with this so-called quantum chaos conjecture by Bohigas and Giovanni and Schmidt, they say that if you take a domain with chaotic classical dynamics, then the eigenvalue statistics is given by the GOE. And then on the other hand, in the integrable case, is given by this Poisson statistics. So these two models are sort of parallel. You can think about this random potential. So it will give you, well, I don't know what, it's not completely correct. I mean, it's not completely one-to-one correspondent. But roughly speaking, what they say is if your eigenvector are sort of delocalized or is flat, then you will have the random matrix statistic. If the eigenvector are localized, you get Poisson. So this is, yes?
So this is a sparse, the matrix in this model is a sparse matrix?
Extremely sparse.
Extremely sparse.
Yes.
And you expect the same behavior?
It's not I expect, it's everybody. Yes. But everybody expect, but nobody can prove.
For a random sparse matrix?
Oh, for sparse matrix, some sparse matrix we can do. But it's not this sparse. Okay, there's a degree of sparseness. So this is beyond what we can do. But we can do some sparse case.
What is the degree of that?
The degree has to be the degree divided by the number of vertices. So if the number of vertices is n, the degree has to be n to the some power alpha, and alpha is between some numbers. I forgot. Okay, and of course then the conjecture is degree 3 is enough, but we can't do it. Okay, so yes.
Is it true that you like questions?
Yes. Yes.
Apparently, the random matrix theory might tell you something about the behavior of eigenvalues.
Yes.
But what about dynamical properties? If you think of, trying to exhibit diffusive motion or something.
Oh yes.
Is that something that you can also, in some sense, map to a problem in random?
The random matrix, if you look at the evolution of random matrix, you will also get some sort of diffusive behavior, but not, the diffusive behavior is a bit more complicated, but it's diffusive. I think that was done by Erdős and Antti. No, where they are. Oh, so you can also get the diffusive behavior in random matrix. But then the two behavior may not be identical, but it's diffusive. Okay. All right. So now now I change a little bit. So now we always talk about the matrix, but on the other hand, in the big community of physicists, they like to talk about this kind of model. Is you take a model e to the minus beta n. You take a potential v. This v can be if v is quadratic, then it's Gaussian. But you can take some arbitrary polynomial, even analytic function or continuous function. So take this model e to the minus n trace of v of h dh. So now you try to introduce some sort of correlation into your problems. And now you introduce it in a different way. It's not the same as this change from Gaussian to independent. So you take to the trace of v of h. Now this is called invariant ensemble because in these ensembles, you do a change of variables, then because the trace it doesn't change. So now this one you take this one, you can diagonalize these measures. You diagonalize these measures, you will get this means you integrate out this orthogonal group, then you will get a problem like e to the minus beta n times h of lambda. And this h is called energy or Hamiltonian. The Hamiltonian is this v of h, because now this trace v of h will becomes v of lambda I, which is quite obvious. But there's something much less obvious is when you integrate the orthogonal group, then you introduce a Jacobian factor. The Jacobian factor will exactly become this log interaction between the eigenvalues. So this is log interaction between the eigenvalues, and this is called the Coulomb gas, and Dyson called it Coulomb gas. And so this e to the minus beta n h of lambda. So now if you look at this problem, now this is a classical statistical physics question, and you can forget about there's no more matrix. The matrix just completely disappear. It's just n particles in a line. Then you ask the statistical physics of n particle in a line. So this is the question you're asking. Now, if you take the v is a Gaussian case, you take v is quadratic, and then this was a classical GOE, GUE, and GSE, and correspond to beta equal to 1 to 4. And then for this question, you can also ask that if the local statistic of the lambda is independent of v. So this is another universality. You ask the question, previously you asked a matrix, and now here is still a matrix, but the matrix depends on this potential v. You can ask if the law is independent of v. And then, so this is another class of questions, and you can ask this for beta equal to 1 to 4, or you can ask for this for general beta.
Don't you want to distinguish now between local and global regime?
Oh yes. When I say the statistics independent of v, I mean the local statistics.
Well, maybe you should explain.
Yes. Oh yeah, that's right. Yes. If you look at the global statistics, okay. So if you look at global statistics, then if you look at the equilibrium density, so v will be this is equilibrium density. Then the equilibrium density is just minimizing the energy. The minimizing the energy. So let's go back a little bit. So just a second. So allow me to do that. So if you take this one, you want to ask the distribution of this one, and this guy, sort of to minimizing this. So roughly speaking, you think about there's a density times this, and there's a log of x minus y, and rho x rho y. You want to minimize in this density. So in minimizing this density, so it's this minimization problem. And this minimization problem, you will get the solution rho of x. And then this rho of x, in general, it can be completely general. It can look like that. And then sometimes you can have another interval. And so it can be completely general. But on the other hand, the conjecture says if you look at inside here, then it's independent of v. So this is another class of problem. But this one you don't have a match. It's not really a metric ensemble, but it's really a one particle classical statistical physics system. And now the historically one did a lot of this with beta 1 to 4 and using orthogonal polynomial method and with lots of progress. But our main interest now, why are we interested in this question, is mainly because if you take a Wigner semicircle law, it's like that. Okay. So now all these all these conjecture are sort of restricted to the global law is like that. And you want to do this case is because you don't want to prove universality, just always semicircle. No. So you want to do something else and try to see. So the message is you have to do the problem and just look at the local structure. You should not look at too much the global structure of the eigenvalue. So this is is there a way to understand the problem? Just look at it locally. So this is a question. And then understanding this problem locally will help us to, because you can. There are also other metric models. It's not semicircle. It can look like that. For example, if you take a random matrix H and plus the diagonal matrix D, and D is V1. For example, if you take this model, then clearly it's not going to be semicircle. It's going to change. But then can you still say inside they are still the same?
What are the V's there?
V is random variable, V1 to V, and these are random. No, okay, so the idea was the following. If you take a minus Laplacian plus lambda V, so this is random Schrödinger equation. So you want to show that this go to GOE. Okay. But you can ask the question if I take a Wigner, or you take a Wigner or whatever. If this go to the GOE, you can ask this question. But you know that it's not going to be semicircle, it's going to change. So if your theory are restricted to the semicircle, then you cannot go very far. You have to be able to understand the problem in some sort of local way in order to make progress to this universality conjecture. Okay. All right. So the theorem, so here I'm trying to describe you the newer result. The newer result is the technically quite important. Is this one? Is the single gap universality. This means it's not just that the universality says if you look at the gap behavior, the average gap behavior is universal. Now this one says if you look at just one gap, every single gap behave exactly the same. And this one, mathematically this is quite difficult result because even in the Gaussian case, even the GOE, you cannot prove this by explicit formula. So I want to say that because you're thinking about GUE and GOE, one have explicit formula. But even with explicit formula, it's very difficult to do this case. In the case of GUE, this is a calculation done by Terry Tao. And this was actually in the same year. So it's not a trivial calculation. On the other hand, here says it's a completely general statement. It's true for all the Wigner ensemble, it's true for beta ensembles. So this was a general result. And the other one says
depends upon beta, but independent of V.
Yes, depend on beta, but it's independent of V. So this is so all the universality means it has to be independent of the global behavior, roughly speaking. It depends on symmetry class characterized by beta, but it should be independent of how your system global behave. So this is the message.
What are beta ensembles?
Beta ensemble. Oh, sorry. I think this is my trouble. It's all these are the same name. These are called a Coolant gas, and it's also called a beta ensemble. Sorry, this is it's because they use this beta as a name. Sorry.
So with that beta less than 1, why are you restricted to beta greater than 1? Is that just something technical? Or is
this is okay. This is something technical. Actually, if we allow some average, we don't need this beta bigger than or equal to 1. So this is a technical this is technical reason. I can explain to you later on. But also one more thing I should say. I expect this second theorem can go all the way to beta positive, and this one I'm not so sure. But then if you allow some average, then we don't need beta bigger than or equal to 1. So it's a technical reason. It's not an intrinsic reason. So and then I will tell you why it's technical. It's okay. So now and then there are lots of previous results, and so I don't really have time to mention. And then also in the case of edge, the edge universality people did this a lot, and stuff from Soshnikov, and there are many, many results. But I think that what we are emphasizing is that the way we are approaching the problem is sort of get the all cases, we get all these, both this beta ensemble, this is the case, and this Wigner ensemble case, we can do the both cases. Okay, so then I already said this. So what's the significance of our result? And by the way, here also the beta case in the edge is also done by Christian Nepru, Wright and Virac, and there are various differences in the assumptions. So I don't want to go to the details of the comparison, but roughly speaking, I want to say that of course, but I think I should say that in their case they cannot deal with generalized Wigner ensemble because their method is strictly beta ensemble type argument. Okay, so now the reasons I think well, at least from my point of view, our method are interesting is because the proof are much more conceptual, and it depends on a few concepts. Maybe the estimate is difficult, but at least the underlying reason and the philosophical reason behind this are very simple. And so let me try to explain why, what's this. Okay, and then the main reason we did all these cases because we are trying to we try to prove universality, go beyond the semicircle and go beyond, because the universality should not depend on the global laws at all. And I was very happy to find out that actually in the article by Freeman Dyson in the late 60s, and he cited a question by Uhlenbeck. I talk about this in the Dyson's birthday, and the Uhlenbeck asked the question: if the global law is if random matches give one global law, why do we believe the local law is universal? And so the answer to this reason is because the reason there's a local universal because everything, there's universalities because everything is local. So it's very, very important to have a method which is a local method. Okay.
What is so special about the gap distribution? If you take other things.
Oh, what's the
why is the theorem sort of for that very particular observable, so to speak?
Oh, yes. In the old statement is always if you take an interval and you count how many the gap distributed in the histogram, then this is correct. And here it says if you fix the index I, then this one single gap is correct. This is very technical. For physicists, there's no reason these two things has to be different. On the other hand, mathematical is quite difficult, and then you will see that the method we are using there will turn out to be important for some other purpose. So this is one main reason. And the other one is you find that the single gap is actually the gap is very stable object. On the other hand, if you ask the individual eigenvalue, it's much less stable. And in many cases, for example, in some of these cases, the gap universality will be there, but the eigenvalue you just keep on moving. Yes. All right. Okay. So the idea I should check the time. Oh, I see the time. Okay. So the idea of the proof. Of course, I'm not going to give the proof. So it's roughly speaking, the idea is the following. So if you have a one-dimensional statistical physics system and you have an energy, and then if you want to prove something universal, it has some universal behavior. If you learn some statistical physics, the first thing you try to do is prove the uniqueness of Gibbs measure. You always try to do it because what you are trying to prove is basically uniqueness of Gibbs measure in one way or the other. It's this kind of statement. But uniqueness of Gibbs measure, now here has two problems here. Here because you have a log interaction. So this means every particle will interact with everyone. This is one thing. And the second thing, of course, this is a continuous system. And the third thing is when the particles come close together, it's very singular. So you have this kind of technical question. But still, it was our strong belief that once you understand this problem from a statistical physics point of view, in So this is what we try to do is the following. So you look at, you condition on the particles outside, and you look at what's happening inside. So inside, so you fix the interval I, and then, so this inside the red particle is from L minus K to L plus K. So you just look at you take a certain region, and you want to study this one. And now you think about outside are your boundary condition. And then the question is, now you have a Gibbs measure with a boundary condition with interaction given by this log. And then the question is, under what class of boundary condition you have a unique Gibbs measure? If you can prove this uniqueness of Gibbs measure, then you solve the problem. On the other hand, so this was, roughly speaking, this was our idea. The idea was you look at, and now this is sort of more mathematical way of writing the problem, and I don't want to go into here, but roughly speaking, I just want to show you a picture what's going on. It's because what you are trying to do is you have a statistical physics system, and this is the global density, and here is another global density. It's a different system. You have a different potential V, then you have a two different systems. All right. So you fix your boundary, and you look at your probability measure inside. And here, again, you fix your boundary, you look at your probability measure inside. And now you want to say, this Gibbs measure and that one, in the limit are the same. Of course, in the limit are the same, there are various questions like, of course, you first have to shift this problem. You have to compare them, and you have to dilate them so that they are living on the same interval. So you have to shift and dilate so they live on the same interval. Okay. Yes.
Are you always conditioning at the endpoints there are two particles?
Ah, yes. Wait, this is not, so this is not completely. So suppose you have think about you just take a case of 5 particles. So now if I want to study these 2 particles, so I give you this location of these 3 particles. Okay. So if I give you location of 3 particles, then this means these 2 particles can go from here to here. So this is the question. So you fix this problem here. Now the other one, there's another 5 particle here. So this give you the, actually it's different color. Okay. So this is another 5 particle here. Like this. Then again, I fix these 3 particles. Suppose I fix these 3. Now I want to look at these 2. If I want to compare these 2 problems, I first have to shift this guy to this guy. And then I have to dilate this one so that they are in the same interval. Now, in the Gibbs measure, then this means these particles, when it hit this one boundary, this is the leftmost you can go. And this is the rightmost you can go. And now then you can compare the 2 Gibbs measures.
So you fix the total number of particles
yes.
in the interval?
Yes, I fix the total number of particles and the interval. And also I have to fix the location of the particle outside. Because this guy will interact this guy will also interact this guy, and they will also, there are lots of interactions. There's lots of complicated. So compared with the classical Gibbs measure problem, this one has both singular and long-range interaction. So then our theorem, what our theorem say basically is we give a classification of the boundary condition, and then it tells you that what are the boundary conditions so that it will give you uniqueness of Gibbs measure. It cannot be all it cannot be all. You need some condition because you can imagine that suppose you want to study these few particles, and then if they are allowed here, and they are allowed here, they are in trouble. And compared with this one, you have one particle here, and then the rest are all very far away. Then there is no reason these 2 has to be the same. So our uniqueness roughly says if the boundary is not too crazy, I don't know how to say it. If the boundary is not too crazy, then it's unique. And then we spend lots of time just to find out what is not too crazy. So it's not. So this was and this one. And so that's why, but this actually we can show that this not too crazy set has a very big probability, and so that's not a problem.
I mean, if you have
yes.
short-range interactions,
yes.
it would be obvious, or not?
Not exactly, because this is continuous mesh. This is continuous system. I don't really know. Maybe it's. I think maybe the answer is. And also maybe the answer is you have the short range. If you have a short range, and non-singular interaction, I think the answer is probably easy. But our case is this is wrong and this is wrong. But this I think is yes. Yes, yes. Oh, it's not just we are using that. We are using the log. We are using the interaction. We are using the interaction has to be log. It has to be like that. And at least the short distance behavior has to be log. And the large distance doesn't matter. But short distance, singularity has to be log. Okay. So this was the. And then maybe you may say that, well, I'm only interested in matrices. I don't care about this statistical physics. And so now let's go back to matrix. And then you will find that in the study of matrix problem, you were actually using similar method actually. So this was the. So this was the probabilistic version of this quantum unique ecology. But so far we only proved the local version, and we are hoping the global version. I think it's correct, but anyway. So this was. So now here you take eigenvectors. You take eigenvector, normalized eigenvector of the Wigner matrices. And then you, so you take any, so this is eigenvector ui, and then you take this eigenvector and you project, so you take two eigenvectors j and k. And then you project this eigenvector onto any fixed direction. So q is a fixed direction. And then you, this times square root n is because this is the right scaling, otherwise it's wrong. Then you find that you take any two, it's not just two, you take any two eigenvector, then actually this will converge to a Gaussian, independent Gaussian. And this is for arbitrary j and k in the bulk. We are not talking about at the edge is also correct, but so far, the edge, it's a lot more work has to be done. So we haven't done it. So, but I think it's all correct. So this eigenvector distribution, it actually becomes independent Gaussian. So this was. And now, once you have this eigenvector distribution of independent Gaussian, then you can get the so-called this quantum unique ergodicity. Quantum unique ergodicity, so now here's a statement of quantum unique ergodicity. So you take an eigenvector uk, and then you look at the component. And then you take any set A, you just take the average of this eigenvector. You take the average of this eigenvector over this set. Then it has to be equal to 1. That's the if you sum over all the component, of course, it's equal to 1. But now if you sum over a small subset, it's also equal to 1. And if this is true for all subset, then of course, then it just means completely flat. But you don't want to say it's all subset because all subset you can also get one element. You get one element, it cannot be correct because there's a fluctuation. So at least there has to be certain size in order it to be correct. So if you average over certain size, if this size is big enough, then it's 1. It's really 1. And this is the code is probabilistic local QUE. And so this is correct. And then, so you may think that, the reason we make such a big effort to study this eigenvector question is it's not because we just want to study this eigenvector question. And that's because depending on how you want to look at it, either from a philosophical point of view or from a technical point of view, you want to understand the eigenvector. And now let me try to give you a reason. So this is the reason behind the reason we are trying to study this question, this eigenvector question. So the basic tool we are using in study a random matrix is by looking at green functions. And this is very different from, if you look at the paper by, I think either Terry Tao and Wu, or this, what's this? Rashini and what's the, Roman, what? Ruderson, yes. I think I'm getting old, even name I start to forget. Or Ruderson. And their approach is very combinatorics. It's also the so-called they also call it geometric approach. But for us, we always look at green function. Now you look at green function of a matrix, and the reason we look at green function is because I studied from the day one of my PhD thesis. It's already look at green function all my lifetime. So I always look. I was also a postdoc here with Tom, and of course we are looking. This is the first thing we look at anyway. And so you take a green function, and now you take a green function, then you compute the trace of green function, and then this becomes 1 over z minus lambda, and z is this complex parameter. Oh, so this, of course, this is sign is wrong, right? Okay, I apologize. And z is e minus I eta. Okay. Now, so you can see that if you take a semicircle law, if you think about your distribution of eigenvalues are given by a semicircle law, then you can also take a semicircle. You also take the Stiger transform. Then the semicircle, roughly speaking, says this trace of green function will converge to the semicircle law. And then in the classical case, this eta is order 1. This is what the Wigner theorem is exactly this precisely this statement. Okay, so now what we are trying to do, we want to put this eta as small as possible, because this eta determines how precise I can understand this function. So you should keep in mind that this lambda j has a space in 1 over n. So you have an eigenvalue here, and the typical spacing here is 1 over n. And then the eta is roughly the size of windows you try to analyze the problem. So if you want to understand the individual eigenvalues, the eta has to go below 1 over n. Once you go below 1 over n, you start to see the individual eigenvalues. Okay. All right. Now, the one way we try to understand the eigenfunction behavior, you see, if you look at the green function, but instead of look at the trace, you look at each component, A. Suppose I take component A and A. You can think about this A is just 1 or 3 or 5, whatever. So then if you look at the expansion into the eigenvalue and eigenfunctions, then it becomes summation over j lambda j minus the z, and the numerator is eigenvector component at A squared. So you look at this GA of z. If you can understand this problem, then you understand the eigenvector. So you understand eigenvector. On the other hand, you understand the eigenvector with a summation over j. So the green function has understanding of eigenvector in some average sense. So in some average sense. And you cannot get to one eigenvector. There's just no way you can understand one eigenvector from this expression unless you can take this eta less than 1 over n. But once eta less than 1 over n, then it's very singular because you are approaching these eigenvalues lambda j very, very precisely. So this object will be terribly fluctuating, and it's very, very unstable object. So there's just no way to control this one. There's one way to control this object is take expectation, because expectation you just integrate out this lambda j, and so that distribution of lambda j, then this maybe this singularity will disappear. But on the other hand, the distribution of lambda j, you know nothing. You don't know distribution of lambda j, and so you cannot compute expectation of this one. And then if you cannot compute expectation of this one, you cannot take this eta less than 1 over n, and then you don't know about each individual eigenvector. So it's a problem. And that's why that's why we can prove the delocalization, because as long as eta bigger than 1 over n, then the object is relatively stable. Then we can understand. But it's difficult to go beyond 1 over n. And so this problem bothers us for a long, long time. I think for many years, for a few years. And now, on the other hand, if you start to think about a question, I like this Wigner's sentence. If you approach the problem in a simple-minded way, you always get the right answer. And so you think about it. You say, oh, gee, why are we so stupid? Because the distribution of eigenvector is extremely stable. It has to be like orthogonal group. It has to be in some way like orthogonal group. So the eigenvector should be much more stable than the whole green function. There's just no reason why the eigenvector will be so bad. On the other hand, if you look at eigenvector, then it's very difficult to study the eigenvector, because if you remember the perturbation formula of a matrix, all this, you differentiate the eigenvalue, you get eigenvector. You differentiate eigenvector, you get even more singular. So it's worse and worse and worse. So now this is something very strange. It's in principle they should be very stable like an orthogonal group. On the other hand, the eigenvector is very singular, and how can you deal with that? So the idea was, this was finally find out. Sorry. I didn't. Okay, so let me explain why is this, and then I'll come back to the how we deal with eigenvector equation. So now we can deal with this this QUE. So this actually will bring in a new tool, and because the reason this will bring in a new tool is because of the following. It's because we previously, there are two objects we are using to study the universality and of matrix. One is a green function. This green function I've been talking about for the last 10 minutes. And the other one is Dyson-Brownian motions. And I will mention this I would describe what's Dyson-Brownian motion later on. And now there's one more tool. This eigenvalue, eigenvector distribution given by this orthogonal group. Okay, so this, we expect this will have some important consequences. So, but before I do that, I'll show you why we can analyze the eigenvector. And then this was, so in a way this was some coincidence and some accident, and then we find that something was computable. So if you look at this Dyson-Brownian motion, so this is called a metric Dyson-Brownian motion. It's actually, maybe one should call it the matrix Ornstein-Uhlenbeck process. The Ornstein-Uhlenbeck process, you take a differentiation of an object given by the Brownian motion and minus itself. This is the Ornstein-Uhlenbeck process. The only difference here is instead of one component, now you take a matrix. You take a matrix and evolve by the Brownian motion, and then you normalize this. You have a drift term so that you keep a Gaussian. So this one will have a Gaussian as invariant measure. So this is a Gaussian as invariant measure, and then you can solve this problem. You can solve this problem explicitly, because now this is a linear problem with a Brownian motion. If you solve it explicitly at any time t, you find the solution is the initial data, in linear combination of initial data and the Gaussian. So the solution of Ornstein-Uhlenbeck process is always a linear combination of initial data and the Gaussian. And the Gaussian, in the case we are talking about GOE, so it's GOE. So you want to think about this as so the solution of this one, you can think about this solution of this one is the initial data plus some noise. So this metric Ornstein-Uhlenbeck process is always the solution of initial data plus noise. And then, so by itself, this will not be a useful tool. But Dyson made the following observation: is now you compute eigenvalue flow. The eigenvalue has a flow. The eigenvalue has a flow which is very, very nice. It looks quite complicated because the eigenvalue intact with each other, and also there's also a Brownian motion term. But the important thing is the eigenvector completely disappears from here. There is no eigenvector here. So eigenvalue has an equation by itself. You can solve this equation. Okay, I mean, I can solve this. This means the solve means you can prove the way opposing it. And now here the beta equal to 1 is because this way opposing of Dyson-Brownian motion is for beta bigger than or equal to 1, because otherwise they will start to cross, the eigenvalue will cross each other. All right, and so if you want to study beta less than 1, there are some approximation you have to do, and which tend to be much more complicated. And then there's a Dyson-Brownian motion about the eigenvector. So this is about eigenvector, and this equation was derived also a long time ago, but nobody made use of it. And the reason is it looks like a nightmare equations. So this means you differentiate the case eigenvector, it will depend on all other eigenvector times the Brownian motion with a singular diffusion coefficient, and then with the drift term, which is even more singular. Okay, so if you look at this lambda k minus lambda L squared, and this equation, if you look at this equation, you will not want to, you will not try to understand and try to solve. Or you may want to try to understand, but if you want to try to estimate this equation, it's just a bit crazy because they are square here. And also, there are also Brownian motion here, so it looks like a terribly, you see there, everyone is interacting with everyone else, and each vector has an n component, and then you just has a nightmare equations. Okay, now the key observation is actually this equation. There's a very simple consequence. Now, before I said it, so what this means is you can solve this metric ensemble process by you first solve the eigenvalue equation, and then given the eigenvalue, then you can solve the eigenvector. So this is okay. And now, I think okay. So now, the eigenvalue equation of Dyson Brownian motion is easier to understand because the Dyson observed that the eigenvalue equation has a Gaussian as the invariant measures. And now once this is a Gaussian as invariant measures, then you can ask the question how fast it approaches the equilibrium. And then what Dyson says is this time to local equilibrium is n to the minus 1. So Dyson has this, what he says is eigenvalue. If you look at the, in a way, Dyson already understood this universality question because the question is the semicircular are actually will happen later. What's important is that the local behavior will first reach equilibrium much faster than the global equilibrium. So I regret that I didn't read his paper when I was young enough. And so actually we even find out this paper after we prove the theorem. But then we find out he already said that you will reach local equilibrium very fast. The local equilibrium times 1 of n, and the global time is 1. So it's a huge difference. So locally, it's reach equilibrium very fast, and then we can prove that. So then we show that it reached local equilibrium very fast, and now yes.
Similar for any hydrodynamic limit that locally
Yes,
faster than
that's right. Yes, of course.
But I mean, is the Dyson Brownian motion sort of even more than?
Oh, it's very fast. It's very fast. It's very fast, and so and also you see when Dyson it's. I have to say that I'm very impressed by physicists, and because when you say reach local equilibrium very fast, what is local equilibrium? Because right now your Gibbs measure are interacting, and it's long range and short range has singularity. You don't even know what's local equilibrium. But in any case, he say you reach local equilibrium very fast, and it's correct. And correct is because what we are proving is with high probability. Its local structure will be correct, and so that's how it's done. And then I think I still have some 7-8 minutes, and then but then there's a question now. Once this become n-1, there's also initial layer from 0 to n-1, and you want to bridge this tiny initial layer, and bridge this tiny initial layer. In the old day, we try to do all kinds of methods, and there are various methods: reverse heat flow, Green function comparison, or you use Terry Tao and Van Woes for moment theory. But at the end, we find that it's completely trivial. At the end, this bridging of initial layer is completely trivial. It's just Ito's formula. You take Ito's formula, you compute it, and it's trivial. And this was very strange. So how come it's something so trivial? We didn't think about this in the first time. And the reason is the following. So now you take a function of metric element, and then you find a smooth function. Forget about all these technical conditions. Anyway, the function is smooth. And then you find that if you look at the expectation, any function of the matrix, and compare with time t and time 0 under this metric Einstein-Uhlenbeck process, then for time less than n to the minus 1/2, there's almost no change of this expectation. So this was. The proof is quite simple. Once you have this, we put this local semicircular as an input. It's just by Ito character. There's nothing. Just compute Ito formula, and that's it. And then the reason is you have to believe that something like this can be correct. the reason is the following. We look at Dyson-Brownian motion. We show that for a large class of initial data, even though initially it was wrong, but very quickly it's already correct. So because it's a diffusive process, so in the short time, it immediately reaches equilibrium. But then if the short time immediately reaches equilibrium, then you cannot prove that at time 0, this initial data didn't change. Because if you prove it, then your theorem is just completely wrong. It's contradictory. And the reason it was correct is because there's no contradiction, is because in this problem, we didn't just use Dyson-Brownian motion. We used this matrix. So the matrix structure tells you that it didn't change up to time n-1/2. On the other hand, Dyson-Brownian motion tells you already n to the -1 is already correct. And so that's why the initial layer didn't change, and there's no contradiction. Because you just look at Dyson-Brownian motion in 2 different ways. And so that's why it's correct. Okay. So finally, I want to say how we analyze these eigenvector equations. The eigenvector equation, I have 5 minutes. So the key observation is the following. You look at this, you go back, sorry. I apologize for this. I should have. So look at this equation. You want to study this equation, which is almost like, it's just very complicated. But then if you do the following, if you take any eigenvector, you take any fixed unit vector, you compute the quadratic moment, the second moment. Then you look at its evolution equation. And now this lambda, all the eigenvalues are fixed. You're given all the path of the eigenvalues. Then you take a derivative of this one. It becomes the random walk equation. So this is a random walk equation. You jump from point j to point k with probability 1 over lambda j minus lambda k squared. I mean, here I do a little bit rescaling because I don't want to do all these n factors, so I did a little bit scaling. So now, so a second moment of the eigenvector is actually given by a random walk in random environment. And this is a key observation. And then, so once you have this random walk in random environment, and then this...
Environment given by the eigenvalues?
Yes, environment given by the eigenvalues. So the eigenvector, the moments of eigenvector is a random walk in random environment with a coefficient given by eigenvalues. So once this is correct, then we look back to our study of the singular of this single gap universality. We have to study exactly the same equation. It's exactly the same. Exactly the same up to some technical points. I don't want to talk about these technical points. So then you find that, of course, this one, lambda j minus lambda k, can be very singular. But as long as we can control their singularity when they're close to each other, we can actually use the classical Diogenes-Moser method. And this is in the recent paper by Caffarelli and Chen and Vasur, and to prove that the solution of this equation is Herder continuous. And now from this, so what's the significance of this Herder continuity? The Herder continuity tells us that this quantity uj of a squared, if you take expectation, then it didn't change in j. So the Herder continuity tells you, because if you look at the green functions, you know the average behavior in j. But the Herder regularity tells you that it's the same for AVJ. So this means now you understand for fixed j. And that's the key, how you understand for fixed j. So now we understand for fixed j, and then there's still a question that even if you can compute a second moment, second moment, you don't know it's a Gaussian. So if you want to know something is a Gaussian, you need something more. And then this part is more complicated. It's not complicated. I mean, it's also, this part needs some algebraic reason, and actually we can also do it. But the key is this Herder continuity give you the input that this is correct. So if you think about it, it's a little bit surprising that, for example, you can think about your problem, just flip a coin of every metric element. And then you want to understand the eigenvector. But in order to understand this eigenvector, you have to go back to the Diogenes-Moser method. This is sort of unexpected. And now, so finally, I want to make some short comment about some possible directions. And then because I don't have much time, and then so I'll just go quickly. So of course you want to study a more general class of matrices and matrices, and there are various types. It depends on what's your taste. And some of these problems already there are people are working on it. So in various cases, and also there's one case there's one thing I was quite interested in myself is the statistical applications. This was because there are lots of applications of random matrix in the biology, in the finance. Well, I'm not sure I'm not sure if you study this, you will make money in stock market. And so, but most likely you will lose. But still, we can do it theoretically. And the third thing is, we expect that this method will also get us away from the mean field type models, and then we will be able to do the band matrix, at least in the case of the band, is fairly fat case. Okay. Also, I'll stop here. Thank you.